So any questions about the previous class? So everything understandable? And probably once during my class, I think there may be one surprise quiz. So surprise quiz means that I do not announce the quiz, beforehand. And usually the surprise quiz is when the attendance is the lowest. And also usually we lock the door because KakaoTalk your friends to come over here to, right? But not today. So today, attendance rate is okay, but sometimes very few students appears. Usually the university festival during that time, the 축제 기간, is most likely that we are going to have a surprise quiz. And surprise quiz only covers like 10, maybe 20 points. So not big enough. But, to change your rank. But if you happen to be on the borderline, like A plus between A or A between B plus, then in the particular case, maybe 10 or 20 points is big. So it can change the grade actually. And other than that, I don't check the attendance. 평소에 출석 안 불러요. And 출석 actually doesn't count. So only case that substitute the attendance is surprise quiz. And it's a very simple problem. Usually write your name. And maybe your student's serial number. But even for that very simple problem, I found that there are some students write my name. So in that case, you cannot get the 20 points. So you have to read the problem very carefully. So we have been discussing the property of a Hermitian matrix. So Hermitian matrix is such that, as a property, such that H dagger is H. So dagger means transpose and complex conjugate. So transpose is in Korean, they say is 전치, and complex conjugate is, I think it's called 결례복소수. In my time, when I was in high school, it was defined as a 공액복소수, but I think does it change? I don't know. What does that mean by 공액? I didn't know that. What's that? It's a 공 means the same, 공통 공, and X is actually the price. X수 할 때 X. So that means I think the complex conjugate is the same absolute value with the original number. So that's the reason why it is called 공액복소수. But I think they changed all the terminology into Korean, and the it's like a couple, right? A couple or correlated numbers. So it doesn't matter. So I think it probably is meaningful too. So if it is Hermitian, then if we have say A dagger is A, then it does have a very interesting property. If for A lambda, 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 right? Formation matrix, the eigenvalue problem. Matrix A, the eigenvalue problem A lambda equal lambda has the following properties. Number one, eigenvalues are real numbers. For lambda I is different lambda j, delta ij. So I told you about the, okay. Someone, turn off the light here, this light. I don't think you can see the screen clearly. 앞에만 불 꺼줄래요, 누가? 이게 스크린 안 보일 것 같아서 잘. 맨 위에 거? No. Not that, this one. It's tricky, isn't it? Can you see the screen clearly? It would be nice if you have turned off the light button. So, this is Kronecker delta, right? So we studied this. This is 1 when I is same as j, and 0 when I and j are different. So just in case, let me just write it down. So delta ij 1, 0, different. This name called Kronecker delta. Identity. This is called completeness. And final properties, when we have this I, lambda I, is A. It's a spectral theorem. So the last property is very important because using that, you can represent the function of matrices. for example, so this is very important properties of Hermitian matrix. So can I move on to the next page? So for example, if you like to find a square, the square of the matrix A is actually A times A, right? But A can be represented by the spectral theorem. So we can write down as the following: lambda I, lambda I, lambda I, J, lambda J, lambda J, lambda J, right? So that is from spectral theorem. Then you just sum over I and sum over J, lambda I, lambda J, right? So this is basically inner product. And what is this? What is this variable? Inner product between lambda I and lambda J is when I and J are equal, then they are 1, right? When they are different, 0. That means when I and J are equal, it survives. Otherwise, it goes 0, right? So this is basically delta ij. So at the end of the day, we have this. Just sum over I, lambda I square, lambda I, right? Initially, we have a sum over I and sum over J. Sum over I and sum over J. But this, the inner product between lambda I and lambda J, forces the summation vanish when I and J are different. And they only survive when I and J are the same, right? So even though the initial summation is for I and J, but final summation will be just sum over I. And lambda I, lambda J equal lambda I squared. Are you following me? Can you follow me? Okay, good. Then what about lambda A cube? You can do it as a homework. It will be I, lambda I cube, lambda I, lambda I. So you can check it as homework. Also, that is a very good problem for the quiz as well. And etc. A to the n. We call this A to the n. A의 n승. A의 n승, we call it A to the n. maybe I'll just write a to the n. A to the n is simply I lambda I n lambda I lambda I. So we can do a very simple problem, like when a is equal to I'll just let you copy. So this is a very powerful theorem. So you can calculate any power of matrix A if it is Hermitian. So for example, in A 0, 1, 1, 0. Of course, we know that lambda 1 is 1. Eigenvalue is square root of 2, 1, 1, right? And lambda 2 was minus 1. Lambda 2 was square root of 2, 1 minus 1. So lambda 1 is simply 1 over half. 1, 1, 1, 1, 1 half, 1, 1, 1, 1. Lambda 2 is equal to 2, 1 minus 1, 1 minus 1. That is 1 minus 1 minus 1, 1, right? So we can check a square 0, 1, 1, 0, 0, 1, 1, 0, which is 1. How about this? This is 0, right? This 0. Finally 1, right? A square is 1. Is identity. So let's check. So lambda 1 square, lambda 1 plus lambda 2 square, lambda 2, lambda 2. That's basically 1, right? So this is basically 1 to the square is 1, minus 1 to the square is again 1. So this is lambda 1 plus lambda 2 is identity. The same, right? Third power, you can do the same thing, right? It's minus 1 to the 1 is 1. 3 is minus 1 to the 3 is minus 1. So it's going to be A. So what about if I ask you to calculate 1 million times? So if you do not know the specular theorem, what would you do? If you just assuming that you do not have any knowledge about specular theorem, and if I ask you to calculate 8 to be 1 million times, you simply just calculate million times, right? Multiplication 8 times 1 million times. It's not very difficult, right? It just takes time. So I think normally if you take 2a, it takes 1 second. So if you want to multiply a million times, how much time do you think it will take? 1 million second. So anybody can calculate how many hours that 1 million second is? So 1 million divided by 3,600, maybe close to 3,000 hours. 3,000 hours. 1 day is 24 hours, right? So 3,000 hours is like 15 days, 2 weeks. So if I ask you to calculate to the million multiplication of A itself, it may take 2 weeks, right? But so you cannot finish during the quiz. But since you know the spectral theorem, you can still calculate that within 1 second. So that's actually, this example shows how powerful the spectral theorem can be. It can also generalize. General function of A can be written as simply this way. I, F, lambda I, and special case, when all lambda i's are positive or is greater than 0. That means A is positive matrix. In this case, we call positive matrix. Then you can even calculate square root of A. We have done that in the previous class, right? The class, if the all the eigenvalues are greater than or equal to 0, then you can even calculate the square root of A. And previously I have shown that, right? With the special matrix with M. And if you multiply by square root of N and square root of M, it becomes N. If you remember the previous class. So the spectral theorem is really powerful that you can calculate any function of a matrix. So let's calculate, for example, exponential zeta sigma y. So sigma y is a Pauli matrix. 0 minus I, 0. So this is special function appears many times in quantum computing. If you heard about quantum computing, probably you did, right? I mean, it becomes kind of the news these days. So this is a very important property as well. So using this, we can actually calculate that this special function. Exponential I over 2 theta sigma y is, using spectral theorem, it becomes exponential I over 2 theta lambda I, right? You just replace sigma y by lambda I, and lambda I. So in this particular case, sigma y 0 minus I 0, we have done that this before. Lambda 1 is plus 1, right? And eigenvector, normalized eigenvector is 1 over 2, 1i. And lambda 2 was minus 1. Lambda 2 is square root of 2, 1 minus I. So lambda 1 is 1 half 1i, 1 minus I. So it's 1 half 1 minus I 1. Lambda 2 is square root of 1 over 2, 1 minus I, and 1 plus I. It becomes 1 half 1i minus I 1. Perhaps I'll just copy this. Copy. Next page. Paste. Move to the above. So, using this property, we can calculate exponential I over 2 theta sigma y sum over theta with the plus 1, 1 half 1 minus I 1 plus exponential minus I over theta 1 half 1 I minus I 1. Exponential I theta over 2 plus exponential minus I theta over 2. Over I minus I exponential I theta minus theta. This is 2I exponential I theta minus theta exponential I theta over 2 exponential I theta over 2. So actually, in the second semester, you are going to learn about Euler's formula, but it wouldn't hurt to learn this now. Exponential I alpha is cosine alpha, I sine alpha. That's Euler's formula. Probably you learned this in the fractional calculus, right? So anybody who didn't learn about Euler's formula, raise your hand. How many of you are not familiar with Euler's formula? One. So this is probably a good time to learn. Exponential minus I alpha is cosine alpha plus I sine minus alpha is cosine alpha minus I sine alpha. So cosine alpha is 2i alpha plus exponential minus I alpha. Sine alpha is 2i exponential I alpha minus I alpha. So if you are familiar with the Euler's formula, then this is the basic formula. Euler's formula. Exponential I alpha is cosine alpha plus I sine alpha. Probably this is the only formula you have memorized. It's going to be very useful later. Then this is, including this is cosine theta over 2 this is sine theta over 2, this is minus sine theta over 2, this is cosine theta over 2. So it's very interesting, right? So this may be a little bit difficult for you to conceptually, but so it turns out that exponential I over 2 theta sigma y is a matrix formula. So this is basically rotation about y-axis. It's basically rotation about y-axis by z-axis. Z-axis by theta over 2. So you have this x and y, this is z, and this is theta over 2. So this operation is basically you rotate your axis, xy axis, with respect to z axis by theta over 2. So this is one of the most common operations in quantum computing. So I will give you two other homeworks. Of course, exponential I theta over 2 sigma x. Exponential I theta over sigma z. Would be very good exercise for you. So some of you might ask the following question, because the spectral, of course, spectral theorem seems to be a very powerful tool, but we have seen that works only for 2x2 matrix, right? So you can also ask whether will it work for like higher dimensional case, 3x3 case. So let's just check just one case for 3x3. So how about 3x3 case? Say A 1 1 0 1 0 1 0 1 1. So what is the first step? You need to check whether this is summation or not, right? Summation, you take a transpose. Then this column becomes the first row. So 1 1 0. Second column becomes second row. 1 0 1. Third column becomes third row, so 0 1 1, right? So, and dagger is AT, you take the complex conjugate, same as A, right? Because in this case we have only real empty numbers. So this is summation matrix. So how do we find an eigenvalue? Determinant of A minus lambda I, determinant of 1 minus lambda, 1, 0, 1 minus lambda, 1, 0, 1, 1 minus lambda, right? So you need to find the cofactor matrix. So cofactor C1, so we have two entries, so C11. C11 is minus 1 to the 1 plus 1, and this 2 minus lambda, 1, 1 minus lambda, right? Which is minus lambda square minus 1, no, lambda square minus 1, lambda plus 1, lambda minus 1, C12, 1, 2 is minus 1, 1 plus 2, you delete this and this. So that is 1, 1, 0, 1 minus lambda, minus 1 minus lambda. So determinant is what? Determinant is determinant is 1 minus lambda times lambda plus 1, lambda minus 1, minus lambda. So that is 1 minus lambda square minus 1 minus 1. Oh, something is wrong. This, and this is minus 1. There must be 2. I think I made some mistake somewhere. This. Oh, 1. Oh, sorry. The first one I have to delete. Oh, sorry. This and this. Lambda. So I think that is wrong. C11 was not this one. C11 was you delete this and this. So one minus lambda. 1 minus lambda, right? So that is minus lambda, 1 minus lambda, minus 1. And 1, 2 is 1, 2, 1, 1. 1, 2 is so you delete this one and this one. So 1, 1 minus lambda, right? So determinant A minus lambda I is 1 minus lambda, 1 minus lambda, minus 1. Minus 1 minus lambda. So this is 1 minus lambda, 1 minus lambda, minus 2, right? So it becomes 1 minus lambda square minus lambda minus 2. So 1 minus lambda plus 1, lambda minus 2. So it becomes lambda equal to 2, 1, minus 1. So it's not a positive matrix. So maybe we can take a break for a few minutes and then continue. Because, the finding the eigenvector will take maybe about half an hour, and etc. 우리 지난번 수업도 올려놨나 다? 옛날 수업하고 옛날 퀴즈 문제. So we are going to post the previous class note and also quiz problems. And usually the topic I cover is quite different from the traditional engineering math books. So you don't need to buy any books. Just follow my note. I think that will be enough. And we are going to post the previous quiz problems on the web or something, online lecture room, right? So maybe the past 5 years or something like that. So it will give you a good glimpse of look for what kind of quiz problems will be asked. Do homework at home. That's the best policy because usually I ask a quiz problem from homework problems. So cases, and let's say 110, 101, 011. The first case, lambda 1 is equal to plus 2, right? So let's say lambda 1 is A, B, C. Then A lambda 1 is twice over lambda 1, right? Or 110, 101, 011, A, B, C, which is A plus B, A plus C, B plus C is same as twice over A, B, C. So A plus B is equal to 2A. That means A equal to B, right? And second, A plus C is equal to 2B. Let's wait for now. B plus C is 2C. That means B equal to C, right? So that means A equal to B equal to C. So if you normalize lambda 1, it can be simply square root of 3, 1, 1, 1, right? Such that we like to make lambda 1 is equal to 1. So that is, you normalize this, 1 over square root of 3 times 1, 1, 1. The second eigenvalue is plus 1. So I will let you copy. Second eigenvalue, lambda 2 is equal to plus 1. So, say lambda 2 is D, E, F. We have used ABC. So, A times lambda 2 is 110, 101, 011. D, E, F is same as before, D plus E, D plus F, E plus F, same as D, E, F. Is it? T plus E, T plus F, E plus F is same. So T plus E is T. So that means E is equal to 0, right? E plus F is equal to F. Okay. E is equal to 0, right? So D and F are arbitrary. E plus F. Let me see, D plus E. D, oops. No, D plus, but also D plus F is E. That means E is equal to 0, right? So F must be minus T. So lambda 2 can be simply square root of 2, 1, 0, minus 1, right? You can put actually lambda 2 as D 0 minus D, right? But you need to normalize this. Then D is 1 over square root of 2. So lambda 2 is 2D squared is equal to 1. So D can be 1 over square root of 2. The last case, is, can I move on? Or I'm going too fast? If you think I'm progressing too fast, just let me know. I'll try to slow down. Seems like it's okay. So 3 is minus 1. So F, G, H, I. But I can be confusing with the imaginary numbers, so I will change, maybe use different index K. That's okay, right? GHK. So A times lambda 3 is 1, 1, 0, 0, 1, no, 1, 0, 1, 0, 1, 1. GHK, which is G plus H, G plus K, H plus K is minus of GHK. So G plus H is minus G. G plus K is minus H. H plus K is minus K. So that means H is minus 2G. Here H is minus 2K. That means G is same as K, right? And H is minus 2G. So it's like lambda 3 is G minus 2G, G. So g square plus 4g square plus g square is 6g square is equal to 1. So g must be 1 over square root of 6. Oh, lambda 2 is square root of 6. 1 minus 2, 1, right? So let's check. So we obtained all the eigenvalue and eigenvector. So I'm going to move to the next page. So even 3 by 3 can be very complicated, right? So 2 by 2 is indeed a very simple case. So let's summarize the result. A is given by 1, 1, 0, 1, 0, 1, 0, 1, 1. It's Hermitian. Lambda 1 is equal to 2. Eigenvector is 1 over square root of 3, 1, 1, 1. Lambda 2 was plus 1. Eigenvector was square root of 2, 1, 0, minus 1. Lambda 3 was minus 1. Eigenvector was square root of 6, 1 minus 2, 1, right? So lambda 1 outer product is 1 over 3, 1, 1, 1, 1, 1, 1 is simply 1 over 3, 1, 1, 1, 1, 1, 1, 1, 1, 1. Lambda 2 is 1 over 2, 1, 0, minus 1, 1, 0, minus 1, right? So this is 1 over 2, 1, 0, minus 1, 0, 0, 0, minus 1, 0, 1. Lambda 3 1 over 6, 1 minus 2, 1, 1 minus 2, 1 is 1 over 6, 1 minus 2, 1, minus 2, 4, minus 2, 1 minus 2, 1. Okay. Next page. And paste. I like to make it a little bit small. Can I make it a little bit smaller? So let's check. It's not turned off yet, so in a safe mode. So lambda 1, let's check the completeness property first. Three, 2, 6. One of the common multiplier is 6, right? So you can make it 6. 1 over 6. 3, 3, 3. 3, 3, 3. 3, 3, 3. 1 over 6. Oh, no. 2, 2, 2. Sorry about that. It must be 2, right? 2, 2, 2, 2, 2, 2, 2, 2, 2. 1 over 6, 3, O minus 1, 0, 0, 0, minus 3, 0, 3, 1 over 6, 1 minus 2, 1, minus 2, 4 minus 2, 1 minus 2, 1, which is 1 over 6. What is that? What's the element? 2 plus 3 plus 1 is 6, right? How about 2 minus 2 is 0? 2 minus 3 plus 1 is 0. So that is, we have 6, 0, 0. How about the second one? 2, 0 minus 2, 0, right? 2, 4 is 6. 2 minus 2 is 0. So again, we have 0, 6, 0. 0, 6, 0. How about the third element? This one. 2 minus 3, 1. 0, right? 2 minus 2 is 0. 2, 3, 1. 6. So that's identity, right? 0, 0, 6. So which is identity. How about the spectral theorem property? Let me check. Lambda 1, lambda 1, lambda 1, lambda 2, lambda 2, lambda 2, lambda 3, lambda 3, lambda 3, which is 2 over 6, 2, 2, 2, 2, 2, 2, 2, 2, 2, plus 1 over 6, 3 O minus 3, 0, 0, 0, minus 3, 0, 3, minus 1 over 6, 1 minus 2, 1, minus 2, 4, minus 2, 1, minus 2, 1. So first term. So 2 times 2 is 4, right? 4 plus 3 minus 1. 6. We have a 6. How about second? We have twice 2 times 2 is 4 plus 2, right? Minus, minus, plus 2. So 6. How about third one? 4 minus 3 minus 1 is equal to 0. So 6, 0. So 6, 0. How about the second row? Again, this is 4, right? This is 4 plus 2. That is 6, right? The second term. 4 minus 4 is 0. 4 plus 2 is 6. So 6, 0, 6. 6, 0, 6. How about third row? It's a very nice thing. There's 4 minus 3 minus 1, which is 0. Second element. 4 times 2 is 6. Last one. 4 plus So again, 0, 6, 6, which is same as A, right? So A is given by here, 1, 1, 0, 1, 0, 1, 0, 1, 1. So spectral theorem is, we just found out that valid for 3 by 3 matrix as well, 3 by 3 Hermitian matrix. And then after that, you need to trust me that it's going to be true for any n by n matrix. And actually, there is maybe 10-page proof for n by n matrix in the upper class linear algebra class toward the end of the book. So in general, if it is n by n matrix, Hermitian matrix, you do have so before I move on to the next topic, any questions about that? So that spectral theorem is valid for any n by n Hermitian matrix. I only showed for 2 by 2 and 3 by 3, but so the homework is design your own 3 by 3 Hermitian matrix and show the spectral theorem for maybe 3 cases. So if you design Hermitian matrix, 3 by 3 matrix, and how long did it take for me to solve the eigenvalue problem and then find the eigenvectors and then show the spectral theorem? About half an hour, right? So 3 set, maybe hour and a half. And this is going to be a joke, but the best time to do the homework is the best time to do the homework. Stood up when you stood up at the blind date. Stood up means 바람 맞다. So you have a blind date and you are waiting at the cafe, but your supposed to be partner never showed up. So normally what do? Maybe wait for an hour, right? So just doing nothing, but you can do the homework. So you can do the homework, sitting at the table, waiting for your blind date, and calculate using your hand, determinant A minus lambda I. So if you decide to wait for 1 hour, maybe you can solve 2 homeworks. Maybe a little longer, 3 homeworks. And actually, you do not lose anything because you will get the good point at the quiz. So it's worth to get stood up. So don't be too despaired when you you are 바람 맞다. You can still get the good point at the quiz. So any questions about spectral theorem? So spectral theorem is a very nice way of representing the matrix functions. And about 80% of engineering problems are related to the matrix functions. So this is very important. The spectral theorem is actually a very powerful tool to solve a lot of engineering problems. So if you learn this during my class, then it will be very beneficial for your future career. And it is quite unfortunate that the typical engineering math books doesn't cover this. Until you're upper class, linear algebra. So maybe I think worth to be introduced at the earlier stage as early as possible. So we have learned about Hermitian matrix. Another interesting matrix is unitary. We are going to learn about the unitary matrix. U. So unitary matrix is something like definition is following. Adjoint is inverse. That means adjoint of U plus U equal or UU dagger is equal to identity. So for 2 by 2 matrix, the most general representation of unitary is following. U is A0 identity, AIX sigma x, I sigma y, I sigma z, AY, okay, let me just write that more neatly. A0I, IAX sigma x, I sigma y, AY sigma y, AZ sigma z, and A0, AX, AY, AZ are all real numbers, and A0 square plus AX square, AY square plus AZ square is equal to 1. And we call this identity sigma x, sigma y, sigma z as generator of 2 by 2 unitary matrix. Sometimes we call SU2, special unitary. Also, unitary matrix is very important in quantum computing as well. Quantum computing. So in a way, you are learning engineering math and also at the same time, a little bit of quantum computing with a bonus, as a bonus. So let's try to find out what kind of this form is. So A0I, AX, sigma x, IAY, sigma y, IAZ, sigma z is A0, 0, 0, A0, right? Plus IAX, 0, 1, 1, 0, IAY 0 minus I0 IAZ 1 0 0 minus 1. So that is A0 minus plus IAZ AY plus IAX minus AY plus IAX A0 minus IAZ. So let's say define alpha as A0 plus IAC, then alpha complex conjugate is A0 minus IAC. Say beta is AY plus IAX minus beta is minus AY minus AX. So minus beta complex is minus AY plus IAX. So this is actually alpha, beta, minus beta complex, alpha complex. And how about alpha square plus beta square, which is A0 plus IAZ square plus AY plus IAX square, which is A0 square plus AX square plus AY square plus AX square, right? So this is 1. So any unitary matrix, let me see. So you can write down as a unitary matrix as alpha, beta, minus beta complex conjugate, alpha complex conjugate with alpha square plus beta square is equal to 1. Then what is determinant of U? Alpha, beta, minus beta square, alpha square is alpha square plus beta square is equal to alpha square plus beta square is equal to plus 1, right? So if we define the unitary matrix in this way, the determinant is equal to plus 1. So special unitary, so U belongs to special unitary of 2. So special means determinant U is equal to 1. So now check whether this is unitary or not. So what about U dagger? Alpha, beta, minus beta dagger, alpha dagger with the dagger. Is you transpose and complex conjugate. So you first transpose alpha minus beta dagger, beta, alpha dagger, and complex conjugate, right? So this is alpha conjugate minus beta, beta complex conjugate alpha. And so U dagger U is alpha complex conjugate minus beta, beta complex conjugate alpha, alpha beta minus beta complex conjugate, alpha complex conjugate is equal to U multiplied by this, which is alpha square plus beta square. How about this? Alpha complex conjugate beta minus beta alpha complex conjugate is equal to, this is 0, right? Also here, beta complex conjugate alpha minus alpha beta complex conjugate is again 0. And the last element is beta square, beta complex conjugate plus alpha conjugate. So this is 1, 0, 0, 1, right? How about if we interchange the order? Whatever, alpha, beta. So U was defined as alpha, beta minus beta complex conjugate, alpha complex conjugate. U dagger was defined as alpha complex conjugate, beta complex conjugate, minus beta alpha, right? So U dagger, if we change the order, then alpha, beta, minus beta complex conjugate, alpha complex conjugate, alpha complex conjugate, minus beta, beta complex conjugate, alpha is, you multiply this together, alpha square plus beta square. How about second element? Minus alpha beta plus alpha beta is equal to 0. Here. Minus beta square, beta complex conjugate, alpha complex conjugate plus alpha complex conjugate, beta complex conjugate is again 0. The final element is beta complex conjugate plus alpha complex conjugate. So this is equal to 1, 0, 0, 1 identity. So therefore, we can say U dagger is U inverse, and that's unitary. So I will ask another homework. I will let you copy. I think I'm going a little bit too fast. So another homework is design your own unitary 2 by 2. Oh. Homework. Your own unitary. U, which is SU2. Maybe 3 cases will be enough. Okay. What about A is not Hermitian? Another case. Non-Hermitian matrix. Say A, 11 minus 5 minus 2, 10. what about transpose? 11 minus 2 minus 5, 10. So it's not Hermitian, right? And A complex A dagger is same as A. So A is not A dagger. So it's not Hermitian. But there are ways to make a Hermitian matrix. We define M A dagger A. Then M dagger is A dagger A dagger is A dagger A dagger dagger is A dagger A is M. So we can produce a Hermitian matrix out of A, which is M. Let's say M is 11 minus 2 minus 5, 10 times 11 minus 5 minus 2, 10, which is 11 square plus 4 minus 55 minus 20 minus 55 minus 20, 10 square plus 25. 11 square is 121, right? So that is 125 minus 75. This matrix we just covered previously, right? And M is obviously Hermitian, right? So M is Hermitian. There is another theorem, polar decomposition theorem. So non-Hermitian A can be written as A is called U square root of M. U is a unitary matrix and M is A dagger A. It's polar decomposition. It's also covered in, I think, upper class linear algebra toward the end of the year, usually. But that's a very powerful tool too when you have a non-Hermitian matrix, but you like to represent it some product form of a Hermitian with the unitary matrix. Then you can simplify many problems. So I'll first write down the recipe. Number one, find lambda I of M, omission M. And then define psi I as A times lambda I, and epsilon I, you just divide by square root of lambda I psi I. Three, show that this EI be orthonormal basis. Define unitary U as EI lambda I, and show U dagger is U inverse. And then finally check U M for lambda K is A lambda K. So polar decomposition can be a very powerful tool, and it'll take about an hour to follow this procedure. And I think today we covered this too many topics already, right? So how about stopping here today and continue next week? So any questions? If you don't have any question, if you do not have any question, I'd like to stop here today and continue next week.